In this video, I'm going to talk about resistance. Resistance is nothing but it opposes the flow of current. Okay, so the basic property of resistance is it opposes the flow of current. At the same time, another important property is it converts electrical energy into light energy or heat energy and heat energy, sometimes both, sometimes only one. Okay, now there are a few other important points we need to know about resistance. More numerical value indicates the more opposition for flow of current. So if you have a 10 ohm resistor, by the way, ohm is the unit for the resistor. So you can use the omega symbol or you can write it down ohm. So if it is a 10 ohm resistor and 20 ohm resistor, so basically what we are saying, the 20 ohm resistor is bigger. It opposes more than the 10 ohm resistor for the flow of current. Now, the resistance of an open circuit is infinite. So open circuit is nothing but, for example, you have a circuit. A circuit is nothing but interconnection of elements. Okay, so if you have a circuit like this, now if it is open right there, the resistance of this open circuit is infinite. Resistance of a open circuit is infinite, and current flowing through the open circuit is always zero, and voltage across the open circuit need not be zero. So I can clearly see the current passing through this is 0 ampere, but at the same time there could be some voltage across this. In this case, we know that voltage across this must be same as the voltage across the resistor. Okay, I believe those things I will cover them in the later on in future chapters, so don't worry at this point. Okay, now resistance of a short circuit is 0. Say for example, if I short circuit this, the resistance becomes 0 of that resistor, and the voltage across short circuit is 0. So once you short circuit, the voltage difference between these 2 points is 0 volt. Okay, but there could be any current passing through, any amount of current passing through that circuit. Okay, another important point is the property of the resistance is independent of time. Okay, so resistance value does not depend upon the time. So the value of resistance does not change with respect to time, whereas inductive reactance and capacitive reactance, they change with respect to time. So it will act same in both AC as well as DC circuits. Resistance is represented with R measured in ohm, and this is a symbol we're going to use to find the resistance value. Now, how do you find the resistance value of a wire? So if you take a wire, every conductor definitely has some resistance. Okay, what is that resistance value? How do we find that resistance value? Or resistance of this conductor is directly proportional to the length of the conductor. So if you see more length, for sure that resistance value of that conductor is high, and R value is inversely proportional to the cross sectional area. So if it is more thick, okay, so here is conductor A and conductor B. So if it has more thickness, so 1 and 2, the 1 is more thickness compared to 2, so conductor 1 has less resistance compared to the conductor 2. Now if I combine these two, R is proportional to L over A, and R equal to rho L by A. This is rho, we call it as resistivity. Okay, we read it as rho, called resistivity of the material measured in ohm meter. Okay, resistivity, sorry about my spelling, resistivity, okay, measured in ohm meter. Okay, and L is in meter and area is meter square. Now this rho depends upon the what type of material we are using. So in this table you can see the rho value. For silver, rho value is 1.64 times 10 to the power of minus 8 ohm meter. Copper 1.72 times 10 to the power of minus 8 ohm meter. aluminum 2.8, gold 2.45, carbon 4 times 10 to the power minus 5, lead 2.2 times 10 to the power minus 7. So here, out of these all these material, which one is good conductor or best conductor? Silver has low resistance value. Silver has a low resistivity value, not resistance value. So silver is a best conductor. But if I use silver for a transmission line, I mean, it's really expensive. Okay, so we cannot use silver. So the next best conductor is copper. Copper is also not cheap either. Okay, so for transmission lines, distribution lines, we do not use copper. We use aluminum, but it's not pure aluminum. We call that as ACSR conductors. But we use copper especially in electrical motors, electrical generators, and transformers, because the space concern. Okay, their space is limited. So if a conductor has more resistance, it's going to produce more heat. So there is not enough room to disperse that heat if we use aluminum. Okay, so that's the reason they use copper, even though it is a bit expensive compared to the aluminum. Now, aluminum compared to copper, aluminum has more resistivity, so definitely it will have more resistance, but it is a lot cheaper. So that's the reason we are using aluminum conductors in our transmission lines, distribution lines. But at the same time, if you hang a pure aluminum wire between two poles, by the end of the day it will reach the ground, because mechanical strength of the aluminum is low. So what they do, they keep iron bar inside, and they wind aluminum wire around this iron bar, call that as ACSR conductor. So the iron bar is going to give you mechanical strength for that conductor, and aluminum is a good conducting material. Gold is also a good conductor, not better than copper. Carbon is really bad conductor. Lead is also okay conductor. So resistance of a wire we can find out by using this formula, R equal to rho L by A. Now, resistance of the wire, especially conductor, depends upon the temperature. Okay, so this R total equal to R naught times 1 plus alpha naught times T. R total is at the final resistance after temperature rise. R naught is the resistance of the conductor at 0 degrees. Alpha naught is the temperature coefficient at 0 degrees, and it varies material to material. T is the final temperature, so temperature change. Based on this, you can find resistance with respect to the temperature change of a material. In the exam or homeworks, I will not ask any questions based on this, but I want you to know how the resistance value changes in a conductor with respect to the temperature change. Now, here is an example. In this example, I solved for finding the resistance value. A 20 kilometer length aluminum conductor has a cross-sectional area of the conductor is 4 mm square. And what is the value of the resistance? So length is given 20 kilometers, convert that into meters, which is 20,000 meters. Cross-sectional area is 4 mm square, convert that into meter square. 4 times 10 to the power minus 6 meter square. He clearly mentioned it's aluminum wire. Rho value is 2.8 times 10 to the power minus 8 ohm meter. So substitute everything, we'll end up with the resistance value is 140 ohm. In the next example, he gave us the diameter of the conductor. Find the value of resistance of a copper conductor. Diameter of the conductor is 4 centimeter. Length of the line is 200 kilometers. So for copper, rho value is 1.72 times 10 to the power minus 8. Here diameter is given 0.04. This area for cross-sectional area A equal to pi d square over 4. Okay, by using this formula, since diameter is given, we can find the area. So R equal to rho L by A. He gave you length. Make sure convert that into meters. He gave you, we found the area from the diameter. and you can find the resistance value. Okay, 2.737 ohms. Now the last example I want to discuss about, say you have a conductor. Assume that this length of the conductor is 1 meter. Okay, and the cross-sectional area, it doesn't matter, I'm not giving you cross-sectional area. Now resistance of this wire is say 10 ohm. Now what I did, by using mechanical energy, I extended the wire. I didn't add any extra wire. Okay, what I did, I stretched the wire. Now the length of this wire is 2 meters, double the length basically. Okay, so even to avoid the length and area, I'm going to say this is L, this is 2L. Okay, so a conductor 1 has a resistance of 10 ohms with length L and cross-sectional area A. Now I stretched it. I didn't add any extra material. Stretched it to 2L. What will be the new resistance? Let me take this as R2. Find the R2 value. So R2 equal to same formula, rho times L over A. Material did not change from 1 to 2. So rho value is same. So it's going to be rho R1 equal to rho L by A. So I'm going to write down the relationship between R1 and R2. This is 10 ohm. Okay, what I'm going to do, here this value is rho did not change, but length is increased to 2L. How about cross-sectional area? So here when I stretched it, the cross-sectional area is going to go to half. Okay, so R2 value must be, so here R2 value must be 4 times rho L by A. Rho L by A equal to 10 ohms. So the new resistance value is 40 ohms. Okay, when I stretched it, length is doubled, at the same time cross-sectional area is halved, so the resistance value increased 4 times. Okay, I'll stop this video here. Next video talk about types of sources. Thank you.